Um, Welcome everyone to this week Autonomy Talks. This week is a pleasure to have Dr. Collin, who is a senior research scientist working in the rulebooks team at Motional. So something about Anne, she received a Master of Science from the École Nationale des Ponts et Chaussées in France. And then she moved to US, where she obtained a Master of Science in Technology and Policy, and subsequently a PhD in aeronautics and astronautics at MIT. So her research interests include various things. Mostly she works with complex systems, and so mostly under the perspective of modeling and architecture optimization. And recently she has been working on performance quantifications for artificial intelligence systems. And when she does this, she takes into account both the practical and technical sides, but also the sociological aspects of the usage of autonomous vehicles or artificial intelligence. We are very happy to have her talk, and we are very interested about what she's going to tell us. So without further ado, Anne, go ahead. The stage is yours.
Thank you. Thank you so much for the intro. We should also be good on time, so I think you can feel free to interrupt with questions throughout. You don't have to wait for the end. Since it's pretty sequential, it's good to have a good understanding throughout. And yeah, I'm going to talk today about a scenario sampling method that we've developed that's called plain and sample, which is one aspect of behavior specification, and so establishment of a behavior specification and validation. We can talk about how that works with the other things that are needed to design a system. But yeah, here we're going to talk about specifically scenario sampling. So there is a lot of research that's happening in terms of scenario sampling and validating, testing AVs. There are different ways to do it, but here we're specifically going to make the case for scenario-based AV testing. So the idea is that AVs are complex systems, they're difficult to design and assess. So you can't just look at an AV and look at its different individual components and say, yes, this should work out or not. Have to test it. And you can't just look at the functional definitions, because there are AI components that might act stochastically, and therefore you need to try the same scenario, or various scenarios to capture the stochasticity of this behavior. And the other end of the spectrum is just letting the AV run, do its thing, and drive for a very high number of miles, which is one aspect, but it's very inefficient. And so you need other methods to complement and try to arrive at a good idea of the performance of your AV without having to let it run for millions and millions of miles. There is a lot of research on scenario sampling, and there's a really good literature review on this. So this is just a very small excerpt, but it feels like there are two sides, or two main domains within this existing research. One is about coverage. So it's really about trying to mimic what happens in the real world and cover the set of potential situations that your AV could be in. The issue with this is you need the event rates of, how often are you going to be at a stop sign, or how often could you encounter this very specific situation, which is really hard to get if you want to weigh those situations with how likely they are. And it's really trying to cover, so there's no it's not trying to reuse what you already know about the AV when you observe one scenario. And then on the other end, or another domain, is more about adaptive sampling. So here it's really, you have the AV that you put in a specific situation, and you try to find the scenarios that are going to be difficult for the AV. So it's really about stress testing. This is really focused on potential collision situations, and it's very iterative. So, you find a situation that could be difficult, you change your algorithms to make the AV pass this test, and then you run it again. But so you can't really derive an overall performance rates for the system because you change your algorithm all the time. And in both cases, we haven't seen too much research on how either these domains, like sets of methods, work when you change ODD. So AVs are going to have to drive in larger and larger ODDs, and the question is, how do we have to redo everything to validate or test the AV? As an example, you've seen, for those of you who have used U-scenes, there are, these situations that you could encounter in the Boston Seaport or in Singapore Queenstown, typo, sorry, are very different. And so, yeah, these are kind of the questions we're trying to tackle here is, do we have to start all over again? Is there something we can learn about observing the performance of the AV in Boston that can be reused in Singapore, for instance, knowing that it's a very different behavior and map and scenes? And yes, how much value do these learnings have when they're not in the same ODD? So let's go back to why we use scenarios to test an AV in the first place. So the idea is the AV is a black box. So we don't assume anything about how it's coded, and it should work for any algorithm that is used for perception, localization, planning, and control. And so we use scenarios that we pass to the system that we know nothing about, and we observe some distribution of performance scores. And then the idea in the SODIF mindset, which is ISO 21448 about the safety of autonomous vehicles, is reducing what you don't know about the performance. And you choose scenarios to reduce this uncertainty, and then you kind of loop through that. That's kind of the general idea of why we're using scenarios to understand our AV. And so that's what we're going to follow here. Just as an overall, this is based on a paper, I forgot to say that, is online, and that was presented at ICSC 2021. But these are the overall contributions of the paper. So first, we proposed a representation of AV performance test based on a Bayesian hierarchical model. We'll dive into that. And then we also offer a metric to quantify the relevance of a new scenario based on that representation. That's the information gain. So how much information do you gain from a specific scenario? And then based on this metric, we can leverage some really nice properties about the information gain in this situation and use a greedy algorithm to optimize your scenario selection. And then we also have a stopping criterion so that you have a sense of, given what you want to know about your performance, when can you stop choosing new scenarios for a given AV implementation? So let's dive in. There are two main parts of the paper and of the method. One is the plain part and the other one is the sample part. So first we're gonna talk about the Bayesian hierarchical model and how we represent AV performance. And then leveraging that, we can do the optimization, which is in the sample part. So yes, this is the overview of the presentation. So first, the AV performance representation, which is plain. So this has come up in various papers about how to represent the scenario space. And so you can view the scenario space as an ND space, where each of the dimensions is some aspect of your ODD. And so these various coordinates can be based on ODD definitions that have been put forward by different organizations like ABSC, and very quickly, so that the scenario space is extremely large, and that you can't sample, even if the first not all of these dimensions are discrete, but even if you try to discretize them, the scenario space is still very large, and so you don't want to sample every single point in the space. And so what we do is taking as an example city, cloud coverage, traffic density as 3 dimensions is we look at what happens to AV performance given that one of these coordinates is fixed. That's why it's called plane. So you have this hyperplane of the scenario space. And for instance, here, these are all the, it contains all the scenarios in the ODD that are in city 1, for instance. And so that's how we break down the complexity of the space is we take these hyperplanes as levels or nodes rather in the Bayesian hierarchical model. So this is the model we put forward. This is an example. It can have as many hierarchical levels as you want. But in the bottom, you'd have the performance that you've observed about your AV in a specific scenario. And then you order or sort your performance observations within the specific ODD element that you chose for your first level. So for instance, here we chose city 1, for instance. So if we've observed performance 1, 2, and 3 in city 1, that's where they're going to go in the Bayesian hierarchical model. And same for scenario 4 that was in city 2, where we've observed performance x4, and so on and so forth. And the idea is that we can fit parameters to unknown functions for these intermediate unobservable parameters that are sigma and bi BPs. So this means that we assume that there is this governing parameter that defines performance no matter what the ODD element is. And then it influences lower level parameters like B1, which is assumed to govern performance in CD1. And we want to find out what the probability is of having a given performance, a performance given a specific city. Does that make sense? Are you familiar with Bayesian hierarchical model? Should I spend more time on this? Okay, I'm going to continue then. I don't know if silence means yes or no. Cool. Okay. And so just to, I use AV performance as kind of an ideal thing, but so this X is supposed to be some number that has an unknown probability distribution that we're trying to fit. This is where this links with what you might know about the rulebook scheme, which is that you need some kind of metric to quantify AV performance, and that's what you're going to use as your X. Here, so obviously, or not obviously, but that's what the bias is on our side is we have rules that are defined and they're associated with validation scores. And here we focus on a specific rule in the example that I'm gonna talk about, which is number of collisions per scenario. But it could be any metric that you come up with, and we can also discuss how other metrics could work in this. But this is kind of a side note about how rulebooks links with this entire method. So now we have our Bayesian, we have our structured representation of AV performance based on ODE elements. So now how to leverage it to optimize our scenario set. So first we need to define a couple of metrics. First, entropy. So these are, your normal entropy and information gain definitions in information theory. So the entropy of this overarching sigma parameter quantifies how much we don't know about the distribution. And then the information gain about this unknown unobservable parameter from observing those this performance in a scenario set A is defined by the overall entropy minus the entropy given that the performance has been observed. And so to give like a visual sense of what this means, so information gain is the reduction in entropy about overall performance. So for instance, if you have at a given time this prior about your sigma distribution, assuming for instance it's exponential, then when you sample, if you're trying to maximize your information gain about sigma, your sampling is going to try to make this probability distribution as certain as possible. So the uniform distribution is the maximum entropy distribution. So it's going to make it look not uniform as much as possible, which is what we want, because we want to kind of have a good idea of what sigma is so that we can have a good idea of what those BIs are, so that we can have a good way to have inference AV performance in scenarios we haven't observed yet. So I mean, yes, higher information because the entropy is reduced. Now we can talk about submodularity. There's a lot. Has anyone heard about submodularity before? This is a concept that's used a good amount in SLAM, and okay, great. So this is kind of a meta use of submodularity, but in SLAM, this property comes when you have factor graphs and just general conditional independence between several nodes. And so this applies too, except instead of having a factor graph, we have this Bayesian hierarchical model, which also has this conditional independence property. And so here we want to maximize our information gain about sigma given on a specific set of scenarios. And this happens to be monotone submodular because of this Bayesian hierarchical model representation. So the main difficulty is finding a good fit for that Bayesian hierarchical model based on some small data set that you might already have about your AV. But once you have that, this property is intrinsic to the Bayesian hierarchical model because of those conditional independencies. And so there is a greedy algorithm that is near optimal. So it has guarantees about how good it is for this optimization problem, which is NP complete because combinatorial discrete optimization. And so we can walk through how it works specifically for our application. So we need an inference model, and here it's our previously fitted Bayesian hierarchical model that we did in plain. And the idea is that while we get more information, knowing that this information cannot be obtained exactly, it's always approximated to a specific statistical confidence. So until we don't get more information up to that level of confidence, we get our posterior distribution for that sigma parameter for each scenario that we could potentially add to the set. And then we see if that scenario actually increases the information gain or not. And if it does, if it maximizes it, so you maximize your information gain at every step. That's why it's a greedy algorithm. If you were to do the search exhaustively, you would need to compare every set at every point rather than adding elements to the set one by one. But the greedy algorithm is near optimal, so we can do that. And so yeah, we update our set based on the scenario that led to the maximum information gain at this step. And then we continue until we have a zero information gain, which happens when you don't have the submodular, the monotone submodular function theoretically, always increases to a marginally lower and lower level. But given that we have this statistical confidence, at some point it gets to zero for us. And yeah, we're guaranteed in this offline version to have an information gain that's within 33% of the maximum information gain we could get in this selection. So that's a nice plus because you rarely see guarantees on scenario sampling methods that are based on machine learning, for instance. A note about which information gain to choose, because I've this could be applied to this overarching sigma parameter, which is about your performance of your software intrinsically. But you could also apply this to any of those lower level nodes, like the ones that are for a specific city, so that you could tailor your scenario selection to whether you want to know most about your AV performance in a specific city or in a specific weather or some ODD elements that you would have chosen to represent performance in your Bayesian hierarchical model. So we looked at sigma specifically in the experiment that I'm going to talk about, but you can also go to a lower level for more tailored scenario sets for your specific ODD. Okay, and then I'm going to show some results. So we did this with Collin. There weren't that many options to generate scenarios in Collin when we did this experiment a year ago. There's a lot happening in Collin, so maybe we should try again. I'm sure there will be more features. But overall, we had 132 scenarios where we varied the number of traffic participants, the town. And so the different towns that are used represent pretty different driving situations. Some are more urban-like, other more, suburban, almost rural. And then the AV always had this route that changed within a town. So that's also some dimension of this scenario space that we're changing. And so first we have to fit our Bayesian hierarchical model. There is also a lot of work on how to find or which probability distributions to start with for your unobservable parameters in Bayesian hierarchical model. Here we choose half normal distributions. They're called weakly informative priors, meaning that you give something to start with, but you're not imposing a very strong prior. It's very amenable to the update that's done in the fit. And there is some Python package that we used for this Bayesian hierarchical model fit. But after we do that, we see that this is the posteriors that we observe. The bottom one is for sigma, and each color here represents the PIs that we get for each different city. So they're pretty, the probability distributions are pretty different based on which city you're in. And this is a check that you can do to make sure that your Bayesian hierarchical model is not too off. So you check what you've actually observed in terms of collision likelihood, because this is the performance metric that we use, and compare it with the predictive posterior that you would get if you did inference on your Bayesian hierarchical model. And so we see that where it fits the least well is for 0 and 1, but then as soon as you start getting into higher values, the fit works pretty well. So one way to improve it would be to have a larger data set to begin with, but usually you're trying to understand which scenarios to sample, so you might not have a big data set to start with. So this is the part about fitting the Bayesian hierarchical model. And then we use that to sample according to the greedy algorithm to maximize our information. And so these are the results that we get. And we also tried just random algorithms, just like selecting scenarios at random, just to see how it works with our proposed metric and the Latin Hypercube Sampling, which is kind of a basic, or not basic, but it's like the foundation of many coverage-based scenario sampling. And so what we can see first, this is mostly to test the metric. It is expected, hopefully our method should work better than a random algorithm, and it does, so that's good. But the idea first is that we see that the information gain is coherent with what we would expect in terms of the comparison between a random selection and a selection based on Latin Hypercube Sampling, which is the information get that you would get from these are all 5 random samples, it varies a lot. And on average, it's not as good as what you would get with a Latin Hypercube sampling. So that's a good sanity check for our information gain metric. And then when we use our algorithm, we see that the variation in information gain is much narrower, so you have a better guarantee of achieving better information gains, and the difference is mostly towards the end, where you see that the information gain plateaus much faster. So you need a fewer amount of scenarios to get to the same information gain, which is good because simulating scenarios at large scales, takes a lot of computation power. So the most information we can get from the fewest scenarios is always good. And to have an overview of what was in the scenarios that we got. So in total, we had 6 different towns in Kara, but only 4 were represented in the set because we used this overall sigma. So that means that observing performance in some towns gave us more information than in others. And this is what is reflected in the set. And so we learn about our overall performance by observing performance in specific towns and then using the Bayesian hierarchical model to propagate that to other towns. And then we mostly get scenarios where there are 0 or 1 collisions. So this is kind of represents this exponential decrease that we see in the overall set. So I should caveat that this is a bad AV model. It's using the kind of background, what is used in Kara for background agents. So it doesn't have any perception, or it's mostly influenced by the route and the map elements that are varied in the scenario set. So this is not using Motional algorithms. The reason why we get many collisions is because the algorithms used to control the AV is very, very basic. But it doesn't matter for the method because we just assume the AV is a black box. And here we're just trying to understand as much as possible about it, which we do here because we see that it's pretty bad. So that's one learning from the scenario sampling. And then we can stop the sampling when the marginal information gain becomes too low. So here you see that it pretty much plateaus, and so we can stop. And we've learned as much as we could given our statistical confidence. The reason why you would have a higher or lower statistical confidence is approximating the posterior and the conditional entropy to a certain statistical confidence level is computationally expensive. Like it's exponential with the statistical confidence that you actually want to achieve. So the more precise you want to be in that evaluation, the more computation it's going to take. So it's a trade-off. And this is overall what is in the paper. So the contributions we went over, the metric, the algorithm, the stopping criterion. The main advantage compared with other methods is that we have algorithmic guarantees in terms of the optimization, and we explicitly represent ODD in the scenario selection. The main limitation and the toughest part is finding this good fit for the Bayesian hierarchical model fit, Bayesian hierarchical model. And yes, the property of submodularity depends on this representation. And we plan to make more experiments on a larger scale because generating scenarios in Kara then was not possible on this large scale, but that's what we want to do, and then explore what happens with other metrics. We should actually have an internship opening for this, like seriously using this venue to test this information. Yeah, this is the method. So do you have any questions?
Thank you, Anne. This is actually a piece of work that I really liked. I was really happy when you put this paper out. Very interesting. Now, where is the key step? Where is the magic happening? So is that the Bayesian So at some point you have that Bayesian hierarchical model, right? So what allows you to make inferences from one scenario to others, in a sense?
Yeah, so this representation, what's baked in this representation is the assumption that there exists such a sigma that governs everything, your performance everywhere. And then the ODD specific elements like the BIs are kind of modifiers. And so you're representing your, or you're structuring your AV performance, assuming that you can do something given or know something given that you're in this specific city. Or so for instance, here, let me use the concrete ones, the concrete parameters in the Carter experiment. We assume that the number of collisions per scenario is this Poisson distribution that is governed by a different parameter given the city, but that each of these parameters are each drawn from this half normal distribution that is governed by sigma. And then assuming that sigma has this, this can shift. But so there is this assumption that they're all drawn from the same distribution. And this is where the fit can be more or less good. And then the sampling is completely based on the Bayesian model. So you don't look at you use your actual performance to build the model, and then you use the model to sample. So if the model is bad, then your sampling is going to be bad.
Right. So, okay, but then you're saying that model. So you assume that there exists such a model, right?
Yes.
And then you assume that the parameters of this model are drawn from this, distribution that you parameterize somehow, and then you find the best fit based on what?
Based on what you've observed. So you do need some kind of small data.
So you need to bootstrap
yes.
the thing, right? So, so that then you can do the sampling, right? But isn't that a little bit of a circular reasoning? Because in a sense, you are kind of building the model. So you eventually do the sampling based on one model that you fit doing some sampling.
Yes.
And
so, exactly. You're right. Sorry. Go ahead.
And so then I'm wondering, how much sampling do you do to do the fit so that you can save on the sampling that you do afterwards, right? And where do you stop one and start the other?
Yeah, it's actually probably a good experiment to run in the future. But I would say, so the main risk is having a biased sample to begin with. The hope is that you would just have had your AV done like a couple of miles or a small amount of scenarios in different cities. And so if you let your AV drive, you're already doing some kind of representative sampling of what could happen in the actual in life, right? Because you're not biasing your sampling in your sample, you're just encountering situations in your everyday testing, just a small amount, and then you bootstrap your performance based on that. So the idea is that you leverage the small.
Right, but then you are kind of the problem with all this is that you are looking at like the tail, right, of the distribution. That's really what you want to learn from, right? But to learn about, you cannot learn from it because you had to do a lot of testing to get that to those tails.
Yeah.
So somewhere there must be some form of assumption that you make on the behavior in these long tails, right, based on something that you can observe more easily, right? So
right, I would caveat that you're not necessarily trying to explore the tail, right? You're really, that would be the coverage part where you're really trying to get into all possible situations. Here we're just trying to get some representation.
Okay.
And you can also use, for these models, you can also use there is literature on, fitting probability distributions of events, granted that they're for human driven cars for now, but could argue that this should be done for AVs where, number of adverse events per man is following a Poisson distribution. Like this Poisson distribution doesn't come from nowhere. It's also backed by literature.
Yeah. Okay, cool. Thank you very much. Let me, allow other people to ask questions if they want. I don't want to steal.
Is there any question from the audience? If yes, you can simply unmute yourself and ask.
I have a question.
Go ahead.
So Annie, you said that the greedy algorithm will lie within 33% of the optimal solution to the submodular problem, right? Is that okay? Is that another tighter bound that you derived, or is it the same bound, which is like 1 minus 1 by E?
Yeah, that's exactly that bound. So it's from anything that has to do with some modularity. I would refer to like Andreas Krause's papers. Yeah, well, this one, the greedy algorithm, is from before him, but yes, that's that bound.
Okay. Yeah, I was wondering because I think that comes around 36 or 37%. But
good. Wait, let me check.
Okay, so I know I was just wondering if that's a tighter bound which you got or something like that.
That would actually be a looser bound, but let me check the one. It's
yeah.
one
So no,
I
mean, you got the tighter bound, so 33%. So that's what I was wondering. But okay, got it. Thanks.
Any other question? I have maybe one, which is more, let's see if I get it right. But so you said, so this is all assuming a fixed, a fixed autonomous vehicle configuration, right? So, but I know you worked a lot also in the past in component selection, right? And now I was thinking, is there a way in which you can tune this approach in another way so that you can get scenarios which are good to have to actually discriminate between the choice of one component with respect to the other, for instance, thinking about sensors or these kind of things.
Got it. Yeah, I thought, so I have two parts to my response because I thought your question was going to go in another direction. Because I thought you were going to ask about, can you use this to validate, like to reuse information about a previous AV algorithm on a new one?
That was the second part of the, that was where I wanted to go next, yes.
Okay. That's a great question. I think the fit would be, I think it's worth trying. It's just because of these unexpected things that could happen due to the stochasticity. It depends on like how different if it's about algorithms or if it's about a simple, well, even an increase in resolution could lead to some, for cameras, could lead to some weird. Yes, I would say the Bayesian hierarchy, I think this could be a level of the Bayesian hierarchical model, but it would need to be worked out more than just adding a level. So the fit would be difficult. And I think the second part of your question is, so here we're using this to select a set to validate an AV that's fixed, design done. Whereas you're asking if we can use this to select scenarios to change the design of the AV. So I think this falls more into this adaptive stress type of research that exists. That's what I was mentioning here. Yeah, I think it goes back to how you can use this if your AV changes. But you can definitely, sorry, let me take a minute to think about this. You can use this to try to fit your model to an existing AV, I think. So you can use this to maximize your information about your AV. And so this is going to give you the set that leads you to the best representation in a Bayesian sense of your AV performance. And then you would want to make sure that your model of your AV produces that same performance distribution.
Okay, I see what you mean.
For a given AV. So if you change your AV and you want to update your model, I think you need to run it again.
Mhm.
For now.
Yeah, that's a great, I mean, it's an interesting part. I think depending on which side of these approaches you fix and which other you let loose, you can use these things to do certification or to do, you know, you have the two sides of the spectrum, right? That's a very interesting topic. Thank you.
I actually have a question about that on co-design, but I don't want to, we can talk about it.
Let's do that when I talk about co-design. Yeah, that's not, yeah.
Next time.
We can discuss it another time. Yeah. Any other question? All right. If in case you have, I think Anne shared her email in maybe one of the first slides. Maybe you can put that up quickly. Oh, right.
Yes.
Nice. Thank you very much. And great talk and great food for thought. Wish you good luck for the next steps. And thank you all for participating. See you all next week.
Yeah, thank you for listening.
Thank you.
Bye.
Thank you, Anne. Good to see you.
Thank you.
Good to see you too.
Bye.
Bye-bye.